Hello and welcome to the last video on 3D printing for repair. Today we will talk about testing. We will show you different methods to make sure your part was printed correctly and will work as expected. You have printed your redesigned part and removed the support material. You can now proceed to testing its quality before you can install it in your product to then finalize the repair. Testing your part is very important for a number of reasons. First, to avoid injuries or other accidents. You should always keep in mind that 3D printed parts have variations in quality. We recommend you to proceed with caution and do some of the tests we will discuss here before using your product normally with the new 3D printed part. A second reason to test is to ensure the part works as expected and identify any failures from the design. Another reason to test is to estimate if and how long the part will be able to endure throughout time with the normal use of the product. And finally, testing will help you to gather information to improve the design of your part if necessary. So let's get started. In this video, we will discuss three main forms of testing. Testing the quality of the print to make sure the printing process went well and the printer is working correctly, testing specific attributes or requirements of a part, and in-situ testing, which means testing the part inside of the product. As we said before, the quality of 3D printed parts can always vary. This is a downside of the 3D printing process itself. In many occasions, the 3D printer may not be working or extruding the material as expected. A successful print also depends on several aspects, such as the room temperature, the state of the 3D printing filament, and the printing settings. Because of all this, it is important to test the part to confirm the printing process was successful and our 3D printer is working correctly. The first test you can do is a simple visual inspection. Take a good look at the surface quality of the part and check for gaps between the layers or very rough surfaces like the one on the picture on the top right. Also check the overall geometry of the part and make sure no parts are deformed or warped. If you identify any of these problems, we recommend to do some tuning on your printer and verify the printing settings you select match the recommended settings by the material producer on the technical datasheet. Checking the printing temperature and bed temperature are a good place to start. The dimensional accuracy will depend on how well calibrated your printer is, as well as the nozzle size. Verify the most important measurements with a caliper and compare them to the measurements obtained from the 3D model. Keep in mind that slight differences are normal. If you find important differences, we recommend you check there were no mistakes when exporting the STL file. For example, accidentally exporting in centimeters instead of millimeters. We also recommend verifying the nozzle size you're using and to calibrate your printer before trying again. You can also verify the quality of the print by measuring the weight of your part. You can then compare the result to the weight predicted by the slicing software as shown on the image on the top right. Keep in mind that the slicing software calculates the weight of all the material it will use to create the part, including support material. So, when comparing the two weights, consider the loss from the support material you have already removed. If you find important differences between the two, we recommend to verify the extruder of your printer is working correctly and the nozzle has no blockage. In this example, we see the slicing software predicted 9 grams in total and the weight of the part without support material is 8.5 grams. So we can conclude this part was printed correctly. Now that we know if the printing process went well and the 3D printer is working correctly, let's move on to testing specific attributes of your part. These attributes are the same requirements you identified during the analysis phase. They can be mechanical performance or exposure to heat or chemicals, for example. Please look back at your notes to know which attributes you would like to test for. Bear in mind these test methods could require specific equipment in a lab or homemade test setups. We only recommend to do tests of this type when it's necessary to ensure the part can withstand the conditions before installing it on the product. Let's look at an example. If during the analysis phase you identify your component needs to be flexible and perhaps bend on a specific direction with a certain force for it to function, you can consider a 3-point bending test to observe if and how much force it can withstand without deforming or breaking. The test setup on the right is done with professional equipment, but in some cases you can recreate the conditions you would like to test for with simple materials around your home or workshop. You also don't need an exact number in all cases, but an estimate of what your product can withstand. For example, if a part can withstand the force from my whole arm, it can probably withstand the force coming from my fingers. Here are some other examples of tests for specific performance requirements. We see the snap fits on the top left being tested on tensile and compression forces by the setup on the right. On the bottom left, we see an example of a creep test, which helps to observe the degree of deformation a part has after being under constant tension for a period of time. This example shows a homemade setup where the parts are taped to the table on one end and bags of water hang from the other end. Last, the image on the bottom right shows the results for a heat-resistant test. This can easily be done with a normal oven, a hairdryer, or heat gun to see how much heat a part is able to withstand. The third and easiest way to test the fit and performance of your part is by installing it in the product. After installing it, ask yourself these questions and observe with detail. Does the part fit well in the product? Does the part work as expected in relation to other components of the product? And how long do I think this part would last? When observing if the part fits, it is useful to ask yourself, are there any gaps? Can I fix the part properly? Are the fasteners, such as snap fits and screws, well aligned and working? Is the part too loose or too tight? Make all of these notes and modify the part if necessary. When observing if the part works as expected, make sure it fulfills the function you stated during the analysis phase. For example, the part on the left holds the mudguard of the bike properly, and the part on the right is well aligned with the pivoting points and allows the head of the coffee maker to open and close. The last test to do is a failure test. Here you can ask yourself, how many times can the part perform its function before it breaks? This is especially interesting for moving parts. In the example, we measure how many times can the switch turn on and off before breaking. Knowing our component can perform well in several locations will give us an idea of its quality and allow us to identify how to improve it in a following iteration if needed. In summary, testing is useful to ensure the part is safe to use, it works as expected, and estimating the part durability and quality. After testing, you will also obtain enough information to improve the design of your part if necessary. Testing the quality of a print will indicate if the printing process went well and the 3D printer is working correctly. Testing specific attributes will allow you to know if the part can withstand certain conditions before installing it in your product. In-situ testing, or testing the part by installing it in the product, will allow you to check if it fits well, works properly in relation to other components, and if the part is fit enough for repeated use. So there you have it. This was the last video of our series. If you need more detailed information, don't forget to revise our 3D printing for repair guide and other guideline tools.